All right, everyone, welcome back. So I have another example that I want us to do together where we're going to use that kind of geometric power series to create a power series representation for a similar or related function. So we're going to use the sum from n equals 0 to infinity of x to the power of n, which is going to have the sum of 1 over 1 minus x as long as we're on the interval of convergence. We're going to use that power series to find a power series for the function 1 over 2 plus x. And in this example, I'm actually going to show us that we can do this in multiple ways, and depending on how we go about doing this, we're going to have different power series representations with different intervals of convergence. And so for our first representation of 1 over 2 plus x, we have to kind of figure out how can we break 1 over 2 plus x down into a couple manipulations that we could apply to our starting point or function 1 over 1 minus x. And so here I'm doing a little bit of algebra to help us see that. We're starting with what we want to have show up 1 over 2 plus x. One thing we could do is pull out a factor of 2 from the denominator or a factor of 1/2 from our entire fraction. Then what would be left inside of our parentheses or our denominator here is 1 plus x over 2. And that would kind of look like with that factor of 1/2 pulled out, a lot like our starting function 1 over 1 minus x. We would just have kind of plus x over 2 instead of a negative x there. But if we replace that negative x with negative x over 2, then that would get the job done. So here we are replacing x with negative x over 2 and multiplying our entire series by 1/2. So just applying that first step of multiplying both sides of our starting series and function by 1/2 is going to give us 1/2 times the sum from n equals 0 to infinity of x to the power of n. And this constant factor of 1/2 we can bring inside and apply to each term in our series if we want to. And then we have to also apply that same manipulation to the right-hand side of our equation. Just multiply it by 1/2, or equivalently multiply the denominator by 2. So now, at this point, we have a power series representation for the function 1 over 2 times the quantity 1 minus x. But to finish this manipulation off and get to the function we actually want to work with, 1 over 2 plus x, we now have to replace x with negative x over 2. And so going from this line to our next line, I brought in that constant factor of 1/2 to each term in our series, and have made our substitution of replacing the x's with the quantity negative x over 2. And so that gives us 1 over 2 times the quantity 1 minus negative x over 2. But as we saw in our earlier algebraic work up there, these double negatives would cancel out, giving us 1 plus x over 2. And then if we distributed that factor of 2 inside of those parentheses that are left over, we ended up with 1 over 2 plus just x. And so maybe the final thing we can do is simplify the terms in our power series representation for this function, right? Kind of like we saw in one of our earlier examples, that negative x in the numerator raised to the power of n can be split apart as negative 1 to the power of n times x to the power of n. So this is the same as the sum from n equals 0 to infinity of negative 1 to the power of n times x to the power of n. And then in our denominator, we'd have 2 to the power of n multiplied by an extra factor of 2. So we could write that more compactly as 2 to the power of n plus 1. And so here we have our first or one power series representation for the function 1 over 2 plus x. It can be expressed as the power series, the sum from n equals 0 to infinity of negative 1 to the n times x to the power of n all over 2 to the power of n plus 1. And so we can see another way to come up with 1 over 2 plus x is just by replacing this x in our original power series with the quantity negative 1 minus x. Now, if we distribute this negative sign, that'll turn this 1 and this x into positive versions of themselves. We'll get 1 plus 1, which is 2, and our positive x will, of course, give us 2 plus x in our denominator. So now if we apply the same manipulation to our starting series, we can find a power series representation for 1 over 2 plus x. We just have to replace x with the quantity negative 1 minus x. And so now we know if we replace this x over here with the quantity negative 1 minus x, we're going to get 1 over 2 plus x, and we need to make the same substitution in our power series. So that'll give us the sum from n equals 0 to infinity of not x to the power of n, but negative 1 minus x to the power of n. And again, we could simplify this or manipulate it just a little bit by pulling out a factor of -1, or really a factor of -1 to the n. And that'll allow us to rewrite it as -1 to the power of n times the quantity x plus 1 to the power of n. And now we have a second and different power series representation for the same function, 1 over 2 plus x. I want us to kind of analyze our two power series representations and see if we can spot any differences. One thing we can notice right off the bat is, well, our first power series representation was centered at x equals 0, while this one is going to be centered at x equals -1. The other thing that we're going to see, which is going to require just a little bit more analysis, is that these two representations are actually going to have different intervals of convergence. So let's go ahead and find the intervals of convergence for each of these power series representations of 1 over 2 plus x. Let's go ahead and start with our first one. And so remember, the way we created this power series representation was we took that entire series or sum and multiplied it by 1/2, and then replaced x with -x over 2. Well, multiplying by 1/2 isn't going to affect a series diverging or converging. It's just a constant factor that we could put in or pull out. The only thing that may affect the convergence of the series, or really where it converges or diverges, is that substitution or replacement we made where we swapped out x with -x over 2. So remember, the original inequality to describe the interval of convergence was the absolute value of x is less than 1. If we replace the x in that inequality with what we replaced x with in our series, we'll get a equivalent inequality describing the interval of convergence for our new function and power series. So instead of having the absolute value of x is less than 1, we have to have the absolute value of -x over 2 is less than 1. Well, we can kind of drop that negative sign inside and be left with the absolute value of x divided by 2 is less than 1. And then we can multiply both sides by 2 to see the absolute value of x is less than 2. And so, well, if we write that not in this inequality notation, but in interval notation, that'll look like the open interval from -2 to +2. And technically, we need to test the endpoints of this interval to see if we have convergence at -2 or +2. But we can do that really, really quickly because, well, what happens if we plug in x equals -2 here? Our series would turn into the sum from n equals 0 to infinity of -1 to the n times -2 to the power of n all over 2 to the n plus 1. And, well, -1 to the n times -2 to the n is just going to turn into 2 to the power of n. Those factors of -1 kind of double negative cancel each other out. And then we'd have basically the sum from n equals 0 to infinity of 2 to the n over 2 to the n plus 1. We could cancel almost all these factors of 2 out, except that 1 left over in the denominator. And so, sorry I'm a little sloppy here, I'm just running out of space. The terms in our series would always be 1/2. And so we'd be adding 1/2 to itself over and over and over infinitely many times. And that would certainly diverge. And we'd see something similar happen if we plugged in +2. We wouldn't get the cancellation of the -1 to the n out. We would be able to cancel some of these powers of 2 out, but we'd end up with like the sum from n equals 0 to infinity of -1 to the n over 2. And that'll diverge just because the terms in our series don't go to 0. We'd basically just be taking like 1/2 or -1/2, then adding the opposite to it and just repeating that over and over, and that would never converge. So next, let's see what happens to the interval of convergence for our second power series representation for 1 over 2 plus x. Well, to create this series, we didn't have to do two manipulations over here. We really just had to do one. We just had to swap out x with the quantity -1 minus x. And so, well, we can take this inequality that describes our interval of convergence and apply that same manipulation. So we replace the x here with the quantity -1 minus x. We need to replace this x here with that quantity as well. And so that'll give us -1 minus x in absolute value. Has to be less than 1. But again, we could pull out a common factor of -1 or cancel out that common factor of -1 from our absolute value. And then it's going to look like just the absolute value of 1 plus x, or x plus 1, is less than 1. And so for this, we can notice our center for our series is not at x equals 0. it's at x equals -1, and we have a radius of 1 as well. So we could go 1 to the left or 1 to the right. And so that would make our initial interval of convergence look like the interval from -2 to 0. And we could very, very quickly test the endpoints if we wanted to see that the endpoints are also still not going to be included in the interval of convergence. I'm not going to write that work down, but I'll talk about it. If we plug -2 into our power series, this piece will become -2 plus 1, or -1 to the power of n. That'll combine with our other -1 to the power of n to just become 1 to the power of n. And we're just going to get the series of adding a bunch of 1s up, which is going to diverge off to infinity. Similarly, if we plug x equals 0 in here, we're just going to get the series of -1 to the power of n, which won't necessarily diverge off to infinity, but it will diverge because it'll never approach 0, and we'll just kind of alternate between 1, 0, or -1, depending on your starting point, or really how you want to work with your partial sums. That's a whole nother discussion. So the kind of final question is, well, if we have multiple representations for the same function, which representation do we use? Or does it even matter? And well, for that, we can look at the interval of convergence. And what we can notice right away is that our first representation, made by multiplying that starting series by 1/2 and substituting x with -x/2, actually has a larger interval of convergence. We can go 2 more to the right all the way to +2 if we want to use this series to represent our function, while for our second representation, we are restricted to a smaller interval from -2 to 0. And so for that reason, because we have a larger interval of convergence, I would argue that that first representation might be a better or more useful representation. And so kind of the point of this example was to show that these power series representations for a function are not necessarily unique, especially if we have different center points for our power series. And having these different representations can also lead us to having different intervals of convergence.